and PNR. Now, this day we won't be talking about EDA. Today, we will be looking at the basics of AI and ML for engineers. What I'm trying to do is I'm trying to take you all through this journey of how it all started and excuse me, how it all started and where we are right now and how it should be in future. Just a minute, let me expand the screen. All right. So let's get started. Opening and introduction. The brief session roadmap. We will be looking why AI ML right now. Why this is the right time to seek more information and really see what it is doing. Then we'll see what had been the history, and we'll quickly look at the the fundamentals. Then we'll see three pillars of AI and ML. Which is data, algorithm, and compute, which is followed by development and workforce. No, uh, we just don't want to learn everything. We want to learn and we want to apply. So after learning about AML, we want to develop and we want to see what really goes into the workflow, and then we'll see how we can think in and ML, how the paradigm is shifting. We were on to softwares, we were on to if-else statement, and now we are thinking probabilistically. So we'll take a look there as well. Then we'll see AI in daily engineering, how we can use AI in our daily day-to-day works to make it easy and efficient. Then we'll see the trends, and we'll try to look what all opportunities does AI hold. Excuse me. And the next session will be challenges and ethics, and finally concluding by learning path and Q&A. So just to see where engineers stand today in terms of AI adoption. If you go out and you take a look in market, you'll find about 24%, roughly like tentatively 24% engineers exploring AI. They don't use it daily, but they are trying to figure it out, what to use, what not to use. GPT, Gemini, XYZ, there are many things, but still have not like inculcated all these things in their daily life. Then there comes that segment which is experimenting. They know what AI is, and they are trying to use it to increase the efficiency, but still they are experimenting here and there to really find a spot which works very well for them. Then comes the adopting. They have figured it out that yes, this is what I will be using, and this is how I'm going to uh, change my workflow. And they have adopted few of the tools, and then integrating, like you don't have to think twice about it. You have like inculcated all these tools, and it's autonomously doing the work which you should have been doing. And they are the ones who are really getting benefit from the time reduction and being more efficient and resource management kind of things. But if we see 80% of the developers or the students or the engineers still have not like fully gone into using all these things completely in their work environment, and still are in exploring, adopting, or experimenting phases. By the end of the session, we the aim is to understand AI ML fundamentals clearly and master the three pillars of AI and ML, which is data, algorithm, compute. Recognize AI opportunities in the workflow, where we can use it, what we can minimize, what we can optimize, and then the practical tools to start using AI tomorrow, and then understand the limitations and responsible use of AI. Now, why this is the exact time we should be considerate about AI and ML. See, whenever you have to analyze something, the numbers are beautiful example of how the things are performing. If you just see in 2024, not even 2025, this data is from 2024, the global AI market was about 196 billion, and the year-to-year growth was 37%. Chat GPT users 1.8 billion so far, and still growing. And like top 500 Fortune 500 companies use AI in their workflows, and they have already started seeing 10 to 15% of growth, or maybe even more, depending on what kind of application or services they are dealing with. So it becomes very important for us as students to or engineers to know how these things are working, what these things really hold, and why it is important for us to know these things. The very first thing is that these numbers are huge and are improving day by day, are expanding day by day. So if we don't get into these things as soon as possible, we might get left behind. So if we see the timeline of AI, 2010 was the time of early deep learning. We were already doing some regressions, and we were already doing some. Google was already into doing this AI and ML stuff, trying to predict values, trying to classify groups. Then it was 2012 when AlexNet came, and it was the eight-layered convolutional neural network, which was very good at recognizing images, and that really changed the game. Following this, the models became very good at recognizing different images: cat, dog, XYZ. Then 2016, it was AlphaGo when Google DeepMind developed it, and for the first time in history, an AI tool or AI software defeated the world champion in the Go game. Then it was 2020, GPT-3 was already was ready to roll out to the market, and then 2022 is when GPT took up. So GPT generative pre-trained transformers. This really changed the game. Now people started using GPT, which was helping them in their daily life. Now today, if we seek more GPT than Google. Like for many engineers it is like that, but yeah, many more are still on to the way. But if we see how it has changed, like you can get everything at one place. You just have to type in and then just explore what all things are related to it, what all things you can take care of, and what all things you can really implement. So this is the brief timeline in the AI history. Then comes, okay, why engineers must care. So, complex engineering tasks are complex because people have to consider multiple things at once. Let's say chip designing. You don't want a chip which is working in just one scenario. Let's say it is like 25 degrees Celsius, and the chip is working on, say, 3 gigahertz some at some CPU or GPU kind of chip. Now, it's not just you don't want to operate that chip at this particular scenario. You might be using a chip in maybe a desert or a cold area. So, considering all this, we need a chip which is working in all the scenarios. So similarly, when we have complex tasks, we really have to take care of multiple things, And human brain is very good at working at specific tasks, but when this area expands and when you have to take care of multiple things at once, it really becomes challenging. And this is right where AI tools have a slight better edge than us. So they have this complete visibility of multiple domains, and they can really help you look into the problem from different angles. Say if you are doing like chip designing, you can like AI can prompt you, or AI can provide some data which you might not have think of. Coming to the coding assignments, or the software generation, GitHub Copilot is already helping multiple engineers fasten their code generation, or the basis generation. It's not creating like a complete system today, but the speed by which we start our things, right, the bare minimum has increased a lot. And that is the thing which takes most of the time in any production of any software, or any system, or anything. Now, it's not just the development, but the ongoing consumption of product as well. The IoT devices, smart devices, automation things, or maybe your phone app. All these things, they need AI today to like bridge the gap between the digital and the analog world. They can take the data, they can like process it, and they can better present it to for the consumption. Then comes the excuse me. Yeah, then comes the career trajectory. If you see, like almost all the fields are dominated by AI now, because they can get better into all the fields and domains just by training. So it, no matter if you are an engineer, or a teacher, or scientist, or maybe a musician, if you use AI today, you'll have this productivity boost, and you'll have this time, better time management. See, time is the most valuable resource, not the money. It's not anything else, but it's the time. When you have enough time, you can do anything. So with these tools, you can really reduce your turnaround time, or the time to do or execute anything. Now, industry adoption technology, we already see a huge leap. About 87% of the technology related industry are already looking into or have adopted AI. Then finance, no need to talk here. Stock market, predictions, probabilities, all those things are the things which hold the finance system. And the AI is very well capable of handling those things. Then comes the healthcare. If you like, how good it will be if you know that someone has this XYZ disease way early in their life, so that they can take care of it. Then manufacturing, automation, and reducing the time to process all these things, it's already happening, and AI is really helping at all these sub segments of the market. Now, there is a question which is floating like for like many years. Will AI replace engineers? And it's not really like will AI replace engineers, but it's more like the engineers were replaced, but it won't be replaced by just AI. It will be replaced by those engineers who use AI to do their work more efficiently. So that's the thing, and that's what we are holding on to going forward in future. So, what kind of engineer you want to be? Let's like look briefly on the history and evolution of the AI, the three waves of AI. Now, it's not just these last 2 decades that the AI has like yes, AI has grown, but it's not just these 2 decades when the AI had been developed. It had been being in use since 1950s. So if you look at the basis of AI, you'll find this probabilistic modeling, then the loss reduction. These algorithms had already been in our maths since like earlier. days. But it's really the power of compute that has revolutionized this complete AI and ML phase. Symbolic AI was already there in 1950 to 1960s. Then Wave 2 came with expert system in 1980s and 1990s. And then 2010 was the time when deep learning was really picking up and taking things at different places. It's not very, it's not just uh, on chances. If you see the compute graph, it has also increased exponentially, coming from Intel Pentium and now looking at NVIDIA GPUs, which can parallelize the task. Uh, it's very in line with how the AI has evolved as well. So, milestones in the history of AI, the Turing test. So it was a test where a system was given to a person, and the person was allowed to interact with it. And if he or she was not able to identify the difference, whether it is a machine or a human, then that machine passed the test. So that was in 1950s. Then came 1997 Deep Blue versus Kasparov. So IBM computer defeats world chess champion. So it was still not completely AI, but yes, the decision trees and all those things. Computer was very well in exploring all this and was able to do that. It was 2012 when AlexNet breakthrough happened, and deep learning wins at ImageNet sparks revolution. Now the systems were able to accurately identify objects and things in an image. AlphaGo was the first like AI driven a software, you can say, or an agent which defeated the Go world champion. Then 2022 ChatGPT launch, 100 million users already in 2 months. Then came the further versions of GPT, multimodal AI era, GPT V 4V, Gemini, stuff like that. Excuse me. So, what exactly is artificial intelligence? So, when we say that a machine is capable of handling a task which requires human intelligence and is able to do reasoning, problem solving, learning, or language understanding, that comes under AI or artificial intelligence. Today we are just seeing the narrow AI, which is GPT and Gemini, all these things, Claude. So single task excellence, they are very good at completing your questions. So if you see the base of GPT, it's nothing but a model which tries to complete your sentence. You write. Where can I find XYZ? Then it just tries to add the words which holds the most probability in that particular sequence. So that is the narrow AI. The general AI is like human level across all tasks. So it is very good at at doing multiple stuffs at once. And then the super AI, like it's really the sci-fi kind of thing, the future of AI, where it will surpass all human intelligence. And all these things require learning, reasoning, perception, language, and decision making. Now let's see what is machine learning. We saw what is AI, then what is machine learning. Now machine learning, a system that learns from data without being explicitly programmed for every scenario. We have seen when in like today also, if we want to write a software, it will have a for else loop to make the decisions or to complete the loop of the program. So what we were trying to do is to cover all the scenarios at like in by doing coding. But in machine learning, you don't program the machine to cover all the scenarios. It just tries to find the pattern in whatever you feed in, and then it tries to recognize them, and then it tries to classify or like tell the difference, or tell you that yes, this is right, or this is wrong. So That is machine learning. You take a machine, you have the data, you train the machine on the data, and then you deploy it in physical environment to see that yes, how this is working in this scenario, this is working in that scenario, everything is taken care of. So machine learning, most of the time you spend is like preparing the data and then having an algorithm or a convolutional network which will operate on this data to predict something or to classify something, stuff like that. Traditional approach is just if you if you write if else code for like each scenarios, that comes under traditional rule based approach. Now, there is this term deep learning. Now, how it is different than machine learning, or what further it holds. So, when you have neural networks with multiple layers, right, and each layer is responsible for identifying something different than the other layers, that comes under deep learning. So if you just see a normal workflows or a normal flow chart, how it works, you have an input. The layer one tries to identify the edges in that image. Layer 2 tries to identify the shapes. Layer 3 identifies the parts. And finally, layer N, you get that object, what objects are there, and then you get that yes, a cat is present in the image. So that is how deep learning works. You have cascaded layers, which works interdependably and produces the output. Now, why exactly is now that the deep learning is working? Because now you have a lot of data. You need data to train any system, and now you have it digitalized in your laptops, in your computers. You have billions of images, you have texts to learn from, and now you have the compute as well. It's not just chances that the Nvidia has taken off from like 10 times in last few years. So compute is also one thing. Now we are able to perform many calculations per second. And then we have better architectures, better neural networks, better transformers to execute the same task. So if we see AI versus ML versus DL, you'll see that AI is really the superset. Then comes the machine learning, and then comes the deep learning. So all deep learning is machine learning, all machine learning is AI, but it's not vice versa. Now, language of AI/ML. So it's no surprise that Python is the language used in the development of AI and ML, or maybe tracking or observing or doing regressions as well. So 95% of market share in AI ML, it's dominated by Python because it is easy to learn. It has the richest ecosystem. You have good libraries, TensorFlow, PyTorch, Pandas, NumPy. You don't have to really implement multiple things from scratch. You have the infrastructure and the library support. But the other languages are Julia, C++, JavaScript, and R. Now let's take a look into the three pillars of AI and ML. Yeah. So the first pillar is data. Now we have seen that for machine learning or deep learning or any learning task, you need something to learn from, right? So data is the raw material that you need, where you will use the data to train something and get some output. So that is the first pillar. Second is algorithms. Now you have something in mind, you know, you have this and you have x and you want y at the output, but you need some function to operate on x to produce y, right? So that is where algorithms comes in. Different architectures, different neural networks, transformers, right? There are multiple ways you can approach a problem. So that comes under algorithm. Now, finally, you have compute. You have the CPUs or GPUs, which will be working with your like you need something which your algorithm runs on, right? So it can be GPU, CPU, Depends, you need parallel processing. Most probably you'll need parallel processing if you are doing AI ML. So that comes under compute. Now, understanding data. So if you see and if you look around the world, you'll see whatever data is present in today's world, about 20% of this data is structured data, which is present in like databases, spreadsheets, CSV files, SQS tables. Now, this kind of data is very very useful and very easy to consume. You have simple Python libraries. You can simply operate on this data to get what you want to know, and then you can really train your models and do stuff. But this is only 20% of what all data is there in the market. Then comes the semi-structured data. This is like JSON, XML, log files, or emails. So this data exists, but it's not structured. It cannot be consumed as it is. It is there in some structured form, which is easy to extract from. Then is the 80% of the data, which is unstructured. You have like images, videos, audios, free text, social media. So you have all kind of data there. There's no filter on like this is this kind of data or that is that kind of data. You really have to dig into these things to get what you want, and you have to filter and organize your data from like these 80% of the sources. Now, obviously, when you're training something to do some to operate on some task, you want it to do with high certainty and high confidence. And this is where the data quality matters. So if you are training a model to identify a mango and you are expecting some other fruit at the end, this won't work, right? If you have prepared it using images of some other fruit, it won't work. So data quality matters, yes. You need to see what all data you are feeding in. Is it accurate or not? Is it complete or not? Is it consistent with other data sets or not? And then is it relevant? So all these things you have to take care early advance before training a system. So these are the data pre-processing steps, like the most common. The very first one is collection. You can gather data from many different kind of sources, API, sensor files, databases. Then comes the cleaning part. You sometime the data is missing. Sometime you have to remove the outliers. Sometime you have to fix the errors, and then comes the transform. So suppose your data is with some offset, you might have to normalize it. You might need to scale the data. Then encoding, your machine might be working on some different scheme, some different symbolic scheme, and you have data in some different language or some different uh, encoding scheme. So that comes under transform. Then engineer, you need so once you have done these three steps, you need to create meaningful features from the raw data. And then comes the split. So you don't want data just to train your system, but to do validation and tests as well. So this is like a real example of sensor data. You see that temperature data, it's 185.2. The second entry is null, and then the pressure is excuse me, 45.3, then 999, then vibration 0.2. So if you see the first case, the the second entry is not a valid entry, and in the second case, the second entry is an outlier. Pressure cannot be 999, right? And in vibration, there is no second entry. So these kind of challenges are there when you are handling raw data. You face missing values, outliers, different scales, noisy readings. So all these things you have to take care by interpolating or removing outliers, normalizing, smoothing filters. So this this is how you take care of raw data and you convert it into relevant data. Now, algorithms. So in AI ML we have supervised learning where we try to create two sets from data. One is learning set, and then there's a test set, and we supervise the this complete learning scheme. We train the model on learning data, and then we test it on test data to validate how well it is doing. And then comes the unsupervised learning. You want to classify things, you want to find patterns, right? So that comes under unsupervised learning. Then comes reinforced learning. Reinforced learning is when you have a working system and you want to further improve it, and what you do is you create an environment, you have an agent which is working in that environment, and for every task you add a reward signal with the outcome. So that is reinforced learning. In industry uses, you'll see 70% of the time it is supervised, 20% of the time it is unsupervised, and rest is reinforced learning. Supervised learning, again, it's simple. You have data, you split it into two or maybe three, and you have input data plus label data. Right, label data is the test data where you had already identified that whether it is a cat or dog, or whether whether it is right or wrong, and then you train the model on the learning data, and you test the model on test data. Excuse me. So supervised learning examples, email spam detection. You can use email texts, right? Who is the sender? What is the subject? And you can make a system to make a model which takes all these inputs. Then you can test it, because all these data you can prepare and you can bifurcate into learning and test data. You can say that yes, this is a spam mail, or this is not a spam mail. Then house price prediction, medical diagnosis, disease A or disease B, credit scoring, all this comes under supervised learning. Then the unsupervised learning, you just have the input data, there is no test data. You are not really trying to say yes or no, you are trying to find some kind of common behavior, some kind of cluster. You're trying to do some kind of clustering, or you're trying to reduce some dimensions of the data. So a single thing, say there's a motor which is like operating for last 100 hours. It has multiple parameters: the operating temperature, right? The voltage it is operating on, the RPM, XYZ, and all these data might or might not be useful for what you are looking for. So suppose you are thinking that you're trying to build a model which will tell that how much this motor will last. So it will depend on how crudely it has been used, what voltages it has been operated on, or what temperatures it has gone through, right? So that all things can change the lifespan of the motor, but painting a motor might not, right? So just taking a rough example, there can be multiple parameters affecting a thing, and there can be even more parameters. So often you need to reduce the number of parameters you are looking into, because that really reduces the computation. Then the anomaly detection, you have a consistent uh, group of things, and then there is some weird thing coming into it, you want to detect that. So that comes under unsupervised learning. Reinforced learning, again, you have an agent, you have an environment, there's some action, and then with the outcome there is a state plus reward. This reward is positive when the agent behaves as expected, and negative when the outcome is not as expected. So this is very like game playing. It's very good in these things. You train a computer to play a certain game, maybe a Mario. You might have seen Mario. The people have trained machines to play Mario, and you might have seen the video of it on YouTube. Then robotics. So you might have seen that four-leg dog, which is made out of motors and stuff. So that is trained. That has been made possible due to reinforced learning. Then autonomous driving. This is no short, and this is no surprise. It needs reinforcement learning. Now let's come to compute. Compute, we have two kind of major systems, CPU and GPU to do the compute. CPU has like uh, less cores but powerful cores. They are capable of doing complex tasks. But on the other hand, you have GPUs. You have multiple cores, but they cannot handle complex things. But they are very good at parallel math operations. Then combining this, you have cloud GPUs, right? NVIDIA H100, that was the groundbreaking chip from NVIDIA that really took off. So this is what goes into the machines which run these AI and ML systems. Cloud versus edge computing. Cloud computing is when you have a machine learning on like operating on a cloud, and you take the data at the user and you send it to cloud for processing, and then you have the output. Edge computing is like when you have these small models on the device, and there is no need of internet, there is no latency, data stays local, you don't have to ship the data. But edge computing really limits how much you can process. Development and workflows. So in the ML development life cycle is like first we need to see what problems are we working on, what thing are we trying to do. We are trying to do some image recognition, or you're trying to build a model which explains your project very well, or a generic model maybe, right? And then there's data which you need to collect for that particular thing. Once you have the data, you have the data in right format, you need to select a model or algorithm or the kind of thing which you will be training and works well on your data. Then comes the evaluation part. You have created a model, you have trained it, then you evaluate it and you deploy it. Once you deploy it, you monitor it, and if it needs improvement, you reiterate it, or just maintain it. Then there is this ML technology stack. At the base, there is hardware, which is like CPU, GPUs, TPUs. Then there is frameworks, TensorFlow, PyTorch, scikit-learning, and then Hugging Face. Then the layer three is GPT, pre-trained models, GPT BERT. So you can use these models to like reiterate on them for your specific use. And then fourth is the application, that is the use, chatbots, recommendation system, image recognition. So, where exactly you should start? You should start at layer three and four. That is the most common things. You cannot like you mostly you don't have that kind of access. Like you can change the hardware or the framework of the system. Many times, what happens is someone has developed a good system and it has taken a lot of time. You cannot invest that much time on it. So you can take that particular model and reiterate it on it like a little, and have your goals fulfilled by it. Now, the tools and frameworks which you should be aware of or you might need while you are working in ML and AI is like from Python ecosystem, you have like NumPy, Pandas, Matplotlib. So all these things are very good at operating on data and like structuring them. Then ML libraries, scikit-learn, XGBoost, LightGBM. So these are ML libraries, deep learning libraries, PyTorch, TensorFlow, Keras, pre-trained model. Hugging Face is one great example. Then Open AI API, you can use GPT using API calls, cloud platforms, Google Colab, AWS, Azure. Then okay, so if you have to start, you can use Google Colab. It's free, and you have good resources on Google Colabs. You can start with NumPy and Pandas and SCI kit basis or Hugging Face models. Excuse me. thinking in AI and ML. So we'll see what really has shifted from hardware to software to AI thinking. So when we talk about hardware, there is a firm determinism. We expect same input, same output. There's some threshold of tolerance, and then it is the system is bounded by reality, physical laws, and in debugging we measure, we use probes, oscilloscope, right? In software we have logic flows, if then else, decision trees. The software, it is repeatable, right? If you have a bug, it is reproducible. Then there are stack traces, what exactly failed, which function failed, where is the issue. And debugging you do by introducing breakpoints, or seeing the logs or traces, right? In AI ML, this all these things is completely changed. So far, we had never talked in probabilistic terms, right? We never had said that how confident are we? So in AI ML, this is the paradigm shift. Now we are thinking at confidence scores, edge cases, unexpected failures, right? Then deep for debug, we do error analysis. Now coming to the accuracy. So how good is good? Like, is 95 enough? Is 99% enough? How good your model needs to be so that you can consume it? So that really depends on what are you trying to do. It can be medical diagnosis, it can be movie recommendation, it can be fraud detection system, right? In medical diagnosis, 5% of error is too big, right? There are lives at risk. So you cannot tolerate 5% of error. Movie recommendation, yeah, it will work just fine. 5% of an error, it's not that bad. You can have a movie or two which might not work or might not go as well. Debugging in the AI era. So traditional debugging, we made use of stack traces to really backtrace where the error started, right? Then you breakpoints. We introduced breakpoints to execute code like through steps. Then bugs, deterministic, reproducible, and unit testing to verify the expected behavior. In AI ML debugging, this is changed. Error analysis has become which cases fail. Then confusion matrices have become relevant. Feature importance, what matters, and then why did it fail on this particular input? All these questions help in debugging, and this is how you debug in AI ML. Now, how can we use AI in our daily work? If we see, like, AI is now these days, AI is everywhere. Code assistants, right? GitHub Copilot, Chat GPT, Claude, right? All these generative AIs are already helping multiple engineers and developers to uh, write better codes, or maybe if not better, then just write the code faster. Then comes the documentation. When once you come into industry, you'll know that documentation takes a lot of time. You need to consider all those things which might come into picture, right? So documentation, if you have a system or a model which can take care of this, it can reduce your time, like work time, by a huge margin. Then learning and research. Remember there were days like when people used to sit and Google each and every thing and then see various aspects of a particular research, or what they want to learn. Now it has been reduced to some generative AI's perplexity. You can just simply go to it, and then you can just prompt some idea you have or something you want to research on, and it will really provide you the like it will do the thorough search on internet, and it will provide you the data in shorter time. Design automation, CAD, no need to like add more on this. CAD, AI, generative design. Then project management, communication, email replies, auto replies, all those things, they are really improving our life standards and the way we are working daily. So if If not less, then at least they are saving 2 to 3 hours daily if one engineer is using them to their fullest. Code assistance, what it does. So code assistant, it's not always that you are developing a code. Sometimes you have a code, or someone has developed the code, you want to work on it, but sometimes the code is very difficult to understand. AI is very, or generative AI is very good at understanding the code and explaining it to you, then finding the issues which the code might hold. uh, Again, AI is very good at these things. So all these things which are rigid, right? If there is a handbook to that, the AI will become very good, better than you to understand those things and implement it, because it has the memory and it has the wider visibility. Chat GPT and Claude, many people are already using it for the code production, right? To explain the code, debug the code, or just learning the concepts. You can try it online on the Claude or on the site, the Chat GPT site itself. Then once you have a project, you can write docs, because uh, you can provide the code to it, and then you can create readme files very quickly, code reviews, what further you can do, what bugs it can hold. Then comes the unit testing. You can write the test cases for your project. That, so all these things had been made very, very, very simple. Documentation, again, you have a project, you can simply upload the required data, and you can save about 60 to 70% of the time in you spend while creating the documentation. So all these things, I won't go deeper into learning and research assistant, designing, and CAD assistance. So all these things, you can see that yes, AI integrated with these tools will have a faster turnaround time or faster output time. Email and communication, data analysis, and visualization. So yes, there's one thing. So often not many people know coding, right? And sometimes to see the trends, or sometimes to see how a system is performing, one has the data, but one does not have enough coding skills or enough programming skills to visualize it. So these things come very handy in visualizing or analyzing the data. So coming to continuous learning and skill development, first, so suppose that you want to learn FPGA designing. So there can be custom curriculum, there can be adaptive progress, and then right level projects, right? So AI can create paths based on your background, then it can adjust based on your speed, and then you need to practice at your skill level. All these things can be taken care. If we look a day in life before and after AI, so if you see before 8 a.m., read 50 emails manually, debug code for 2 hours, write documentation, attend meetings, take notes, research solution to problem, write weekly report, go home exhausted. That's at 6 p.m., right? So after AI summarizes email, that's 5 minutes. Copilot helps debug 30 minutes. AI generates docs, 15 minutes, transcribes, extracts actions, GPT finds the solution, AI writes report draft. Now, then you can really focus on creative problem solving, and by 5 p.m., you go home, learn something new. So there's a huge difference, and I have been emphasizing this. It's the time which you should be worrying about. It's the time that really matters. So what if you want to get started on AI tomorrow? How you can do it? Very first thing, sign up on ChatGPT, Claude. It's freely available. Basic prompts, you can ask GPT to do stuff, or ask its help in doing stuff yourself. Then there's this GitHub Copilot. Or if you're a writer, you can try Grammarly. It's very good. Then second week you can use AI for one task per day. So see, it's not very easy to integrate it. Sometimes uh, people know what their needs are, right? And not one person can solve all the problems. To solve it, the individual itself has to look where he or she can use these AI things, and where exactly he or she can reduce the time or increase the efficiency of the workflow. So once you have this habit in initial 1 or 2 weeks, then you can expand it to wider problems, wider issues. And then by third month, you can be a really power user. You can do advanced prompting. You have projects within these generative AIs where you do specific things. You can automate workflows. You can train your team to do this. Excuse me. Now let's look at trends and opportunities. What's really hot and where AI is heading. So no surprise, GPT-4 is already there. I think GPT-5 is also being rolled out and is under use in the market. This large language model, they have human level text understanding and generation. They can help you in multiple domains. Then there will be like multimodal AI, text plus image plus audio combined. So now if you see, so suppose you are doing some tasks, well, just presentation creation, if you think now, or the documentation of your maybe final year project, or a project that you have been working as an engineer in an industry, uh, text generation, right, image creation, audio creation, all these things, they are being made accessible by AI. Then edge AI on phones, like in Apple devices, you have Siri and stuff like that, IoT, cars. So that's edge AI. AI for science, you have AlphaFold, then climate modeling, AI agents, open source AI. You can use these models to create your specific version of model which works on your specific needs. Across industry, we see like uh, imaging wise, it has been of great use in healthcare, medical imaging, diagnostics, drug discovery. Then physics, particle detection and simulations, all these things, they have been made like 1,000 times faster. And then astronomy, engineering, manufacturing, finance, all these things, AI is playing a huge role in improving the turnaround time and improving the efficiency as well. Now, what is there? What does the future hold? 2026 to 2030. What can you expect? So, not very uncommon. Every engineers will use AI assistant because excuse me, because if you don't, you'll be left behind. Everyone will be needed to ramp up on AI assistant. Then 50% of the code written with AI help. See, it's not every day you invent something new. It's the it's the use of already invented things and your style and your way of problem thinking and providing solution that really changes the offerings. So 50% of the code written with AI help. AI first design tool became standard. So so far there has been no tool which is completely designed by AI. Like it's a big tool and it has already been used in industry. But yes, that is another milestone. Just like an AI won against uh, the chess player. And then edge AI in every device, phones, car, appliances, wearables, personalized AI tutor. That is another good thing. Like you have not every student is same, so one can have a personalized AI tutor for every skill, and can really enforce custom learning at which scales. Now, let's do a reality check. What are limitations and responsibilities in AI ML? So there are some technical limitations. AI is very data hungry, right? To train something, you need thousands or millions of examples to train effectively. If you just see GPT, there are some billions of parameters it has, which are operating under hood the transformers layer, and then just to train that, a lot has gone in. So AI is data hungry. Then this black box behavior. So with if else kind of reasoning, you really knew what exactly was the system doing or how it was able to do it. With black box, you don't really know what's going inside. You just provide input and then you get a output. So it's really it becomes hard to explain why AI made a specific decision. And when system becomes so big, like there are billions of parameters, it becomes even more difficult to analyze and debug. Then it is brittle. It can fail unexpectedly on inputs slightly different from the training data, and you cannot like foolproof it. There are always failures, and just analyzing it, it might not be that easy. And then it is expensive, just not by compute but power as well. It needs just training large language model costs millions of dollars. So when you're doing something, you should be aware of these limitations, but don't be derated. Now, see the basis and the fairness. AI systems learn patterns from training data, and if the data contains historical biases or underrepresents certain groups, the AI will showcase in its output, and then sometime it introduces some bias. Real world examples, facial recognition less accurate for minorities during due to training data. So again, training data has the effect of how your system will work. If you provide us limited kind of or a certain kind of data and you don't include all type of it, its accuracy reduces. Along with it, it introduces a biasness as well. So so suppose if you have there had been this incidence that there was some engine which was trained on white Americans and it was not able to recognize black Americans. So it has already happened, the biasness and the fairness issue. So solution is diverse representative training data, rigorous fairness testing across groups, human oversight on critical decisions. And your role as an engineer will be to be aware of potential biases, test carefully across diverse inputs, speak up when you see the problem. Now, coming to responsible AI practices, augment, don't replace. You should use AI to embrace human judgment, not substitute it entirely. Then always verify the output, especially for the critical decisions. So suppose you're making a system for healthcare, right? Or you're making a flight system, something. So you should always verify the outputs. AI can be very confident and wrong at the same time. So this is a big issue. Then protect privacy. Never share confidential or sensitive data with public AI tools, and this is a limitation as well. So if you want to do some research which you want to keep private and you want to use the tools, the market tools, that again becomes a problem. So yes, protection and privacy. Give credits and disclose. Do not be transparent what you are using, how you are using, and when AI assisted your work, you should credit it and you should disclose it so that others know. Then keep learning. It has been the constant parameter of for students or engineers everywhere. See, AI will evolve and it is evolving rapidly. You need to understand what you want to do and what you need to learn. Now, your learning path forward, there are a few courses. Andrew NG ML course, then Kaggle Beginners Hands-on ML book. You can then there are projects, predict house prices, classify images, share on the GitHub, and then to specialize, you can create a domain-specific project. You can join communities to work with them and provide your inputs to make existing systems better. So the resources to get started, there are multiple online courses, free courses. There's Coursera, then there's Fast.ai. Google is always there. There's an ML crash course which you can use. To practice, there is Kaggle, Colab, and Hugging Face. Hugging Face has like a huge repository of transformer models. So if you want to create something on top of existing offerings like Llama or BERT, you want to try something, you can make use of these models to train further and provide you some specific kind of output. For books, you can use artificial intelligence, a modern approach, and the 100-page machine learning. There are several communities like machine learning, Learn ML, AI, Twitter, then LinkedIn AI. There are several LinkedIn AI groups which you can follow to get more knowledge and expand your horizon. And then finally, you need to see what really interests you. It can be medical, healthcare, it can be engineering, manufacturing, it can be scientific research, creative arts, or maybe you tell us. So, coming to the concluding slide, the key takeaways are AI ML is accessible to every engineer. You should start today. With the internet boom, there is no reason to be left behind. You should get into these things as early and as quick as possible. Then you should start thinking probabilistically, and you should embrace uncertainty. Soon will be the days gone when you say that yes, this is entirely correct or that is entirely correct, and you start saying like yes, this is certain, yes, I am confident 95% of the time that this can be the output or things like that. So you should start thinking probabilistically. Then you should make use of existing tools like Copilot, ChatGPT, Claude. They really are handy and they are very useful in providing you data or helping you to create some project or something to visualize. Then 2 to 3 hours a day, I won't say that you should start 2 to 3 hours. Maybe 1 hour is also good enough. But the main thing is that you should get started in it as early as possible. And soon you'll see that it will reduce your like work time by 2 to 3 hours a day. Then you need not to like build a huge system from day one. You start small. It gives motivation as well, and then you build habits and you expand gradually. You should verify and you should protect privacy. AI comes with responsibility, and you should be responsible while using it. Then learning never stops. AI will evolve, and so do you. This had been the constant throughout the year, the learning, and it should never stop. So with this, I would like to conclude these today's presentation. Thank you, and I'm open to questions now.
Okay. Do we have any queries? Yes, anyone? Do we have any queries from your side, dear participants? Okay. Uh, so Kripanshu, thanks a lot. It was quite a good lecture, and I just hope that our participants learn a lot out of it, and they will try to take the advantage of all that you have suggested and would follow the instructions you have given, right?
Sure, Sneha. Thanks a lot for inviting me, and it had been a pleasure to present this in front of you all.
Likewise, likewise. It was a pleasure having you on board, right? Thanks a lot.
Thank you. Thanks,
Yeah.
Sneha. Thanks.
Dear participants, before our second session may begin, we have with us Parth Banugaria. I'm again proud teacher to share with you all that he has been our alumni of batch 2012. So basically, Parth has completed, just as I said, her bachelor's from V.V.P Engineering College, affiliated to Gujarat Technological University. He has done his master's from Nirma University. Parth has experience in the semiconductor industry of more than 10 years, and he has worked with wireless leaders in the world as well as he has worked on the architecture side. He has experience exclusively focused on sign-off domain, which includes static timing analysis, which is crucial part of a SoC deciding game changer for frequency and power of the chip. For today's session, Parth is going to give us an idea about AI in the EDA domain and its application. It is a great pleasure to have you with us, Parth,
Thank
and
you.
being in the different time zones. I just am grateful for of all the things, of course, for your session, but for managing the day today, right? This early and joining us for this session.
Thank
Okay,
you.
so are
Thank
you
you.
ready for the presentation?
Yes, I can start.
Sure. Go ahead, Parth. It's all yours now. Yeah.
Okay. Okay. Good evening, folks. Thank you, Sneha madam, for the introduction. So today I'll be covering the basics of design automation and AI application related to it. I have included one very big example of how AI can replace the automation side and how we can achieve uh, the better performing SoCs chips in the coming years. So starting with today's presentation, so basically, as we all know that chip designing is becoming more and more complex. Everybody, as the computation is increasing, more and more cells are added into the SoC, and we have to cross-check whether it is scalable, whether we can actually manufacture it, and there are multiple factors that will affect whether whatever we are visualizing will be turned into a product. So design process has become more and more critical, and more innovation is required here. And the trend is also similar for the coming years. That in the coming years we will see more and more bigger chips, which will have better computation, better performance, better power. Since we all know that uh, the compute demand, the semiconductor demand is increasing day by day. All the products, whatever we see in a day-to-day life, we are adding chips into that, whether it's your appliances, phone, car, everywhere, right? And on top of that, the AI models are one of the biggest consumer for the semiconductor, and the biggest problem for the AI is the computation, the size that they need for the learning of the models and prediction. So, since the semiconductor is required everywhere around the world, it has become very, very crucial that we should have a way to change how we are currently doing the chips, designing, manufacturing, everything. And in the coming years, we have to come up with the new innovation to fulfill these kind of demands. Um, on the traditional challenges, I think the major challenges that we see are the bottlenecks, right? So what we see in the designs versus what comes out from the as a product, as a is there any question?
No, Path, it was a
Yeah.
mistakenly turned on mic. You may carry on.
Okay, okay, yeah, please feel free to stop me if you have any questions or anything. On the traditional challenges, I think the bottlenecks are that whatever we visualize versus whatever comes back as a product, there will be a huge difference in that. So we have to make sure that whatever we are putting into the simulation is proper and it will cover all the cases of the defects. Similarly, a typical design cycle time was huge. It was like it depends on the chip. It was varying from 1 year to 2 years to 3 years, some cases. But now, since the demand is increasing, we have to reduce these cycles, design cycles. And the third is the rising cost. So since we are adding more and more compute, more and more features to the chipset, the price for that product is increasing. So if you, for an example, if you take a phone like 4 or 5 years back, right? You will have a from the phone, you will have a very limited features, right? You don't have all these AI capabilities in camera and everything. But today, if you buy a phone, you are getting all these features, so that that is added as a part of your semiconductor chip, right? It's basically a separate module for doing all these NPU computations. So and by the and in the coming years more and more features will be added in your car, in your appliances like fridge, refrigerators, washing machines, everywhere, right? So we have to basically come up with a way that we can add all these features but with a minimal cost. And due to all these issues, AI ML basically to come up with an automated way of doing all these things has become a very, very crucial. And the application, and it's a perfect time, I would say, to implement the AI in all these kind of design process and everywhere. So I'll basically cover the backend design part of it, how AI and what is, first of all, what is backend design? Backend design is the physical design where we whatever we have visualized from RTL, we will try to put everything into the physical parameters. So we will do first floor planning that okay, which module will sit where. So for example, my memories should be accessible. Let's say if these are my memories, then it should be accessible by all the modules. So it's very important that the floor planning, success of the floor planning is critical, because many modules may be talking to each other, and if we are placing them far apart, then the we might not be able to converge the design. Similarly, the placement of the cells, we have all these flip-flop and cells, inverters, all kind of cells. So it's very critical that whatever we are placing, it is basically at their perfect position, at their optimal position, I would say, so that we can basically converge the design, they can communicate to other modules. The third aspect is the congestion, so and timing prediction. So if we are doing this kind of floor planning and placement, we have to make sure that we are not putting everything into the single area where most of the wires are routed through. So it is very, very critical that we are not doing any kind of this congestion and in this area. And the timing prediction. Timing, I'll cover it in the next slide. And then there is a assisted routing. So when we are doing the routing, my route should not go from here to here. It should be nearby. It should be in a hopped manner, adaptive manner. So all these kind of designs that we do, we call it as a backend design. And backend design has these four important critical steps: floor planning, placement, routing, and timing prediction. So today I'll be covering the example of the timing prediction and the congestion, right? More of a timing prediction and what kind of role the AI can play here. So what is the timing concept? Basically, um, if we if we take any kind of SoC or chip, right? If we open that chip, we will see all these transistors and everything, right? But transistors cannot be a building block of a system on chip, right? SoC. So what is the building block of an SoC? So building block of an SoC is not even the cells, right? So we cannot say that, okay, if I open that, all I will find or sell inverters, buffers. No, we cannot predict that. So what is the building block of any kind of system on chip? So the building block of a system on chip is nothing but a timing path. So what is timing path? Timing path is a flip-flop followed by a logic. Logic can be anything, and cell, buffer, inverter, anything here, and then again flip-flop too. So here it is getting clocked. Here it is getting same clocked. So we have to capture when this flip-flop is launching the data and it is going through the logic, this flop 2 has to capture the data on time, okay, with respect to this clock, the same clock. So this basically architecture is the building block. This is nothing but the digital logic design, right? This building block, this architecture is the building block of every semiconductor product that we see today. Okay, so this is the technique. It's a static. So we cannot do dynamic timing check because we don't know how much coverage we will have. So we consider that all the clocks are working at all the time. Okay, so we are being pessimistic here. So we always do static because dynamic is very, very costly and it is not convertible. So this way we can consider that, okay, my building block of any chip is flop 1, logic, flop 2, and it is driven by the same clock. Okay, now in this building block, but what we can decide is, right? So we can decide the frequency of a chip. So you guys might have heard that this particular laptop, chip is operating at this frequency, or this mobile processor is at this frequency. So what is the frequency? Frequency is nothing but this clocking frequency. Okay. And so what we have to make sure is that if we make it faster and faster, then there will be a saturation that the data launched from this position to this position will not reach on time. If we make it faster, it will not reach on time. If we make it too slower, then again it will be a problem. Okay, so the data capturing at the flop 2 stage cannot be late, cannot be early. Okay, so this building block decides the fate of every system on chip. Okay, any questions? Okay, moving forward. So if we take the static timing analysis, if we take the same building block, what are the terminologies, right? So we call it launch flop. Okay, so this flop is called the launch flop. This is the clock network. So clock could be, they are connected together and they could be connected to a PLL logic. So this is a clock network. This logic is called combinational logic. And then there is a capture flop. Okay, so these are the terminologies that we use. And there is one more, which we call it slack. Slack is a term that we use to make sure that whatever the time at which I am capturing the data here at the flop 2 is early or late. So let's say if it is 0, it is met. If it is positive, it is met. But let's say the slack is negative, which means that I have a violation in my design. Okay, so I'll cover both the aspects to it. Why this data signal, the capture that we capture here, cannot be early, cannot be late. It has to be on time. Okay. Now, this building block, this is one building block of a semiconductor product, but in reality, we will have billions of such combinations. Okay, so this is just one aspect, but if we go and see the chips that we have today, it will have billions and billions of transistors and billions of such combinations. So it's very, very critical that we have to make sure that the data reaching at the flop 2 is always on time. Okay. Now, moving ahead. So setup time. So this is again a terminology that we use for identifying that what if my data is late. Okay. So let's say if I go back and see the time at which we are capturing the data here is late. So what happens? So this is my clock frequency. This is clock usual going. This is typical our digital logic design. And we have a start of a data here. So data is basically, the data is going from here to here, right? And we see that the register window is basically here, right? So data that is coming out is late. Okay. It has to come at this point so that we can capture at this point. Okay. So what effect it will have? Let's say if my data is late, right? I will have a setup violation. What effect it will have? The data must be stable before the active clockage. Okay, that is fine. Setup violation occurs when data arrives late and it will affect the maximum frequency. This is the main aspect to it. So let's say if I'm saying that, okay, my chip works at 100 megahertz. If I have a setup violation, then it will not work at 100 megahertz. It will work at, let's say, 98 megahertz or 96 megahertz. We don't know. It depends on how much late it is. Okay. So we cannot have any kind of setup violations in our design. Okay. And the second aspect too is the hold time. Hold time is early. Okay. So let's say if my data that is captured, that we are capturing here, right, is basically early. So data is arriving early, but the whole window is starting late. Okay. So what will have happen in that case is a similar concept. Data must remain stable after the clock age. Hold violation occurs when data arrives late, and it can be fixed by delaying the logic, basically delaying the logic. But what if I have hold violation in my design? It is nothing but a chip failure. So chip will not work. Okay. So setup violation, I can still reduce the frequency and can make the chip work if we have any setup violations. But for hold violation, it is a red flag. We cannot have a hold violation in the design. Okay, it will make sure that it will basically make sure that the data is arriving late, hence we cannot capture the data. So the logic will fail. Okay, the logic of this building block will fail, and it will fail. If it fails, then it will fail for the whole chip. Okay, any questions? Okay, so moving ahead. So now we have understood the building block. What is my building block of a chip? What kind of, so basically this is again, this is nothing but the flops, right, that we have, flip-flops. So it will have the semiconductor. If you, this is nothing but the transistors, right, connected to each other. So we will have logic, which will have any kind of combinational cell and or nor, all these kind of combinational logic, and then we have a flip-flop too, which is same but capturing the data. So this flop is launching the data and this flop is capturing the data. So this is very simple architecture, and inside all of this is nothing but the transistors. Okay. Now, if I have to make sure my setup time and hold time is met, my chip will work, right? Okay, fine. I agree. But at what temperature, at what variation of voltage, right? That is very important. So the first aspect is the temperature. We all know that transistor operation will change with respect to temperature. As of now, we always do the simulations, everything that we do at a room temperature, which is 25 degrees Celsius. But that is not the real case, right? If we travel from, let's say, from deserted place like which has a temperature of 50 plus degrees Celsius, and we travel to, let's say, Antarctica, which is having, let's say, minus 50 degrees Celsius. So my chip should work in all those cases. Okay. Now it is very important to note here that if my transistors, if my logic, if my cells are going to behave differently with respect to the temperature, how how can I make sure that, let's say, if I have a phone, right? It has a chip, and if I am traveling from, let's say, from equator to North Pole, right? It should work. But that is not the, I mean, theoretically, it will not work because the operation of a cell, operation of the transistor are changing with respect to temperature, right? But that we don't see it, right? If we travel, let's say, from south to north, our phone works seamlessly. There is no issue with it. If we even travel to colder places where the temperature is sub-zero, that is there also my phone works perfectly fine, right? So what we have to do to make sure that this kind of temperature effect uh, does not control the operation, then we have to do the simulation. So first aspect of this building block is that I have to make sure that data is captured on time without setup violation, without hold violation, ranging from minus 40 degrees Celsius to 125 degrees Celsius, or let's say even more. Okay, so if I have to go and check on every temperature, no, that is not possible, right? I cannot check upfront without while designing that, okay, I will start with minus 40 degrees and minus 39. That is not feasible. That is not scalable. That we cannot do. Okay, so multiple combination needs to be considered in this case. Okay, so this is the main aspect that we call temperature, which will impact the operation of the chip. The second impact is the voltage. Okay, so if I consider my building block, and if it's working fine, let's say at 5 volt, what if I give them 3.5? Will it work? We don't know. And that can happen. The voltage variation can happen and it will impact the operation. The cell will behave differently. It will, let's say, if it was taking, let's say, 100 nanoseconds, now it is taking 120 nanoseconds, or even faster if the voltage is increasing. So let's say if I am increasing the voltage, then the logic time was 100 nanoseconds, then it is going to be like 80 nanoseconds. So it is becoming faster, but if I lower the voltage, it might become slower. Now, the voltage control is not always in my hands, right? If I cannot control the voltage all the time. For example, why? The, the argument here would be that, okay, if I am having a phone and I am giving a battery to the chip that is being operated from that phone, it always gives 5 volt, right? What is the problem there? Now here, if all the components, all the modules of the phone uses 5 volt, the phone battery will die in 1 hour. Okay, so we cannot do that. What we have to do is we have to come up with a retention method. What is retention method? Retention method is very simple. Let's say if my phone camera is operating at a 5 volt, but I'm not using camera all the time. So I don't have to give 5 volt always to my camera module, right? If a user is from the software, it is saying that, okay, open the camera, then and then I'll give 5 volt. Otherwise, I'll give 2 volt. It will save my power. It will increase my battery life. Similarly, the screen time, right? Whatever the screen that we see on the phone, it does not have to be on all the time. So it does not need 5 volt all the time. Whenever the user is touching or it's basically moving, at that time only we start the screen. So these methods are called retention methods. Now retention methods will impact the operation of this building block. Okay. If I am giving the same building block to voltage, so I'm asking them to, okay, be ready. We might send the data, okay, but you operate at 2 volt as of now. Now let's say if user is opening the camera, so I'm saying, okay, here I'm giving you the 5 volt. Now you should start operating, but in that case, it may not be exact 5. It may be 4.8, 4.7 volt, right? Because it's spontaneous. So whenever my voltage increases or decreases, there is a direct impact on the cell delay. Okay, it's very simple, it's very proportionate. Okay, if there is a minor, let's say, if my this logic is is becoming faster, then I will have a hold violation here. If it is becoming slower, then I will have a setup violation here. So I cannot have a faster nor slower logic, okay, in the building block. So voltage is a second important factor that we have to consider. The third and the last factor that we have to consider is the aging. What is aging? Aging is the sense that if I bought semiconductor product today, what will happen in 2030, what will happen in 2035, what will happen in so on 2040, right? As the time goes by, the robustness of the cell to operate will reduce. Okay, the throughput will degrade. There will be more, the cell might not work as it should. Okay, so what we have to do is we have to basically consider aging as a very important factor, and especially in the cases where we have a automotive sector. So if I buy a car today, it has a self-driving. It is operated through a semiconductor chip. But let's say after 3 years there is a robustness and the chip fails, then it's life-threatening. We cannot have aging robustness to be more of a impact here. Okay, so what we have to do is when we design this product, we have to make sure that the for a phone kind of products in 5G and all that, we have to make sure that it has to work for 10 years, right, without any hindrance. And for the products like automotive or the space applications or any kind of application that we do, we have to make sure that it works for at least 20 years. I'm just giving you the examples, right? So aging is a very important time. Throughput will degrade, my frequency of operation will degrade. So consistency and prediction is very important. Now, I can do the simulation of temperature and voltage while designing, but how will I do the simulation of aging? Because time is time. Let's say if I want to check what happens after 5 years, I have to make that chip run for 5 years. But I have to, but mark, we have to sell the semiconductor chips. We have to, user has to use the semiconductor chips, right? So it is very, very important that there has to be a way to simulate the time. Okay. So this is a very, very important factor that is happening in today's time. And this aging factor is going to be very, very crucial for all the next generation chips. Okay, any questions here? So now we have understood the three aspects: voltage, temperature, aging. Now if I combine all three, okay, and I have to check if my building block works, then there will be a huge combination, right? Voltage, temperature, aging. So we have to cross-check every item with equivalent other. Okay, so we cannot do that. If we start doing that, there will be a 1 million combinations, and we cannot do the simulation on 1 million combinations. It's very, very costly, and it will take years to complete. Okay, so there is a direct connection on how good my product is versus how good my semiconductor design is versus what kind of selection, so what selection I'm doing for all these three factors. Okay, so if we combine all the three factor, right, we call it one scenario or corner. If you have might heard timing corner, timing scenario. So if we combine all the three factors, then what we get is one timing scenario, and we have millions such combinations. Okay. So there is a direct application for the AI here. What we have to basically ask AI tools to basically make sure that if I have a voltage range, huge temperature range, and huge aging range, I have to give everything to AI. I have to basically ask AI to do the prediction, to learn the models, okay, just to reduce my simulation effort. I want to make sure that I am covered across the values range that I am putting it for the chip design, and I want multiple cases to be covered at once. What does that mean is that, let's say if I have a voltage operating from, let's say, 5 volt to 4.5 volt. Now I do not want to check for, let's say, 4.5, 4.6, 4.7, 4.8, 4.9. And if I add the second decimal point, then it will become 100 such combinations, 500 such combinations, and so on. So what we have to do is we have to make sure that whatever the models that I'm using can do the prediction. Let's say if I give 4.5, 4.7, 4.9, and 5, it should cover all the cases of 4.6 and 4.8. So I can reduce my number of combinations. It's all about reducing the number of combinations. As we reduce the number of the combinations, the time that I need to basically do this kind of chips will reduce drastically. Okay, so I don't have to do the simulation for 1 year or 2 year. I can do it in 6 months, 8 months. I'm just giving you just the example numbers, right? Just to see the impact. So our main target here is to reduce the number of combinations. Okay, but is that enough? Is this the only thing? Let's say if I reduce the number of combinations, what will happen? Right? Will my chip work? Not sure, because there are other factors which will affect the combinations. What are the other factor? The other factor is the power wrapper. Now, all the three parameters, voltage, temperature, aging, are related to power directly. Okay. If I have a combination, okay, and if it is at the higher voltage, what will happen? Higher power can cause the voltage drop or overshoot, and it will directly affect the timing margins. It might become very, very fast. It might become voltage drop, and it might become very slow. We don't know, and it will affect directly the building block. So the data can reach late or it can reach early depending on what we have. What if my temperature? What is the impact of power on temperature? Increased power leads to thermal rise, right? If I increase my power, let's say if I give everything 5 volt in the semiconductor, all the modules of the chip, right? The temperature of the chip will rise and it will slow down the transistors. And then aging. So if I increase the power, it will just accelerate the wear out mechanism. So I have to select the combination of all the three, and I have to consider that the power has to be optimal. Otherwise, what will happen is our building block might work for one case or two case, but over the time, let's say for aging, it will stop working after 2 years. Similarly, in some cases, let's say if the temperature drops below, let's say -10 degrees, it will again stop working. So that is not what we intended here. Okay. Any questions here? And the last aspect is the manufacturing defects. Okay. So, as I have mentioned it previously, uh, whatever we visualize might not be true because there could be multiple things that can happen in the manufacturing. So, how does that impact my operation, right? I mean, how does that impact my logic, the building block that we have here? So let's say if I have designed this particular logic building block and I've given everything proper, but let's say the net, the wire that is connected from this logic to FF2 capture flop is having more kind of a manufacturing defect if it is open, right? Then the signal will not transmit from the stage to the stage. Okay, so it will basically say that, okay, the data will not reach at the flop 2, basically our capture flop. Okay, so it will not reach the data here if it is an open, and if it is a short, then the data will just keep on going here and here and here. Okay, so it is very important that we have to consider the manufacturing defect. Okay, now what is the manufacturing defect has impact on all these three things, right? So the normal wire is continuous and uninterrupted. The open defect shows the break in the wire causing signal loss. So signal will not reach on time. And the short effect does shows as unintended connection. So let's say if there are two wires, one wire is going like this, one wire is going like this, and then there is a short, unintended short happening here. It can basically cause a logic errors. Okay, but let's say if I have intended the width of this wire to be, let's say, X microns, right? Then from the after the manufacturing, it is becoming like, let's say, X1 microns. It has reduced its width, right? Then again, the same problem will happen. I cannot have a proper signal because when I have considered the design, when I run the modeling of SPICE simulations, I have considered X width of wire, and now it is X minus something number X1 width of wire. So signal will not propagate as it should. Okay, so again, there will be a delay in the logic transmission, and again, it will make a semiconductor failure. Okay, so these two effects are directly connected to power, and the manufacturing defect are directly connected to uh, the overall design, overall combinations that we are considering on which we will do the simulation on voltage, temperature, aging. Okay, so what we have to do is basically this is just an example. So we can use any kind of model here. We use all these cells as a node and nets as an edge. We see setup and hold, early, late, basically, and all the three parameters will take temperature, aging, and learns the delay propagation through pattern across the path. So since we have one building block, okay, and we have multiple such building blocks, right? We have to consider that whatever the delay that we are propagating, we have to create a graph for it, virtual graph. If I create the graph, then I will get to know that which particular building block at what particular stage is failing, or let's say it's passing. Let's say if I have a hit rate of 90%, 90% of the building blocks are passing. Then for the rest 10%, I want to see what kind of failure it is happening. So I can see it from timing data on the selected corner. Selected corner is nothing but the combination of voltage, temperature, and aging. Okay. So if I do the graph construction, okay, and if I go back to my initial slide here, what can I see from this slide? Okay, that whatever the reds are there, they are basically failing. Whatever the blue is there, they are basically passing. If there is, if one square is reflecting my building block, okay. Now I can see that there are a lot of failures here, right? So I have to again do the same thing. Okay, I have to identify, okay, what is the cause of the failure? What is the cause of this particular voltage? Whether voltage is the problem, whether temperature is the problem, manufacturing defect could play a role here, or it could be related to any kind of third-party parameters. Okay, if I do that, if I see that, okay, these are my failures, what I have to do is I have to graph construction, then I have to train. Okay, so I have to train my whatever the data that are failing, and I have to do a supervised learning on the non-delays, that how much delay it is taking. Okay, what kind of path it is there, whether it is how long is the path, whether it's like too long, whether the logic route length is too long, then I would have a different kind of problem. Then I have to basically make sure it is properly buffered and so on, right? But here, very important factor to consider is that whenever we have these kind of delay numbers with respect to the type of the path, okay, we have to make sure that in the next cycle, I can predict these kind of delays upfront. Okay. Now, this is one use of using this model. The second use is the prediction. What is prediction? Prediction is nothing but, as I have mentioned, that we have the combination of these three things, right? Voltage, temperature, and aging. Now, one combination, if I'm using, can I predict the second combination from the AI data? Let's say if I, as I've given the example, right? So let's say if my voltage is uh, operating at 4.5 volt and I have given 4.7 volt. Okay, and temperature is mm, let's say 10 degrees Celsius and 15 degrees Celsius. So can I predict 4.6 volt and 13 degrees Celsius? So in between ranges, can I predict it by using the model? It, if I can, that will reduce the combination of all of these scenarios. Okay. Are there any questions? Okay. So what is the benefit of using this kind of AI models? One is that it will reduce the simulation effect drastically. Okay. Let's say if I have previously I had 600 such cases combinations, can I reduce it to, let's say, 100? Okay. If everything scales linearly. If not, then we cannot reduce it as it should. But let's say hypothetically, if everything will scale linearly, we have to consider that can I reduce my simulation effort? So that will basically give me an edge on the time to market. Second combination is it should cover all combinations, right? It should not have like, okay, this is missed, this voltage is missed, this temperature is missed. Okay, this combination with with different power is missed, right? So we cannot have that. We have to consider power across all combinations. We have to consider the manufacturing defect across all the combinations. Okay, and I should be able to use these kind of models doing the SOCs. Okay, so let's say if I do this, what are my next steps, right? Which is very important, because what I have to do if I can predict all of these things. So first is if there are failures, I have to change my design. I have to modify my design, right? First of all, but let's say, can I reduce the number of change? Okay, if I if I take the building block, okay, if we take our building block, if there is a delay, if the signal at the flop 2 is coming late, okay, and I make my logic faster, then there it is coming too early. So the ripple effect should not happen. That if I am fixing late, it is coming early, and if I am fixing early, it is coming late. Okay, so we should do minimal changes in the designs, but we should have very, we should not have any kind of ripple effects. Okay, so whenever we are fixing one such building block, we have to make sure that it is neither early nor late. It is basically coming with the permissible time of the clock edge. The second is the localized fixes. So since the the violations that we see in our design, right? I should be able to do the fixes on it with very, very limited changes only in that particular region. So let's say if I have a violations, then I should be able to do it limited into that bounding box. I do not want to touch any other thing, because all the other components, other cells are working fine. We don't have any issue with it. So we should basically modify our designs only on the impacted designs. Then touch only the impacted design. This is one more very important aspect we have to consider, is that functionality. So functionality is this. So if I am fixing these kind of violations in my design, my logic should not change. Okay. If in my logic box of a building block, that has to be consistent. It cannot change. Let's say if it was transmitting, let's say if it is a combination of inverter and buffer, then if I am transmitting 1, it should come out as 0. But let's say if I have a violation and I did some changes in the cells and everything, then if I'm sending 0 and it is coming out as 0, it should not happen. That is a logic failure. Okay, so there should not be any kind of behavioral change. Okay, and this is new violations. New violations, what is new violations? Okay, so this building block is just for our understanding, right? But this building block is connected to another building block, it is connected to another building block, and so on, right? So let's say if I fix my logic in this design to make sure that the signal is reaching here on time, right? I cannot have a new violation created in the next building block. Now the next building, this flop 2, FF2, can act as a launch flop also. Basically, it is connected to logic and to another flop, logic and to another flop. So let's say if I delay the logic here or make this logic box faster, then it should not create the new violations. Okay, so it is very, very important to consider that whatever the changes we are doing, Okay, let me summarize again. So whatever the changes that we are doing, it should not create a ripple effect. It should basically have either if we are fixing early, it is fixing. It should not create late violation. If it is we are fixing late, it should not create early violation. Similarly, we should touch only the impacted areas. The areas where the impact is not there, we should not touch it. Okay, and since this is like if I am fixing this building block, the violation, new violation should not come up here. Okay, so the ripple effect, the transitioning effect should not happen. So for this application, for one such application, we are creating these kind of AI modules, okay, where we load all these data, okay, that we know for learning process. We can just analyze that data. Okay, we can run any AI module, whether it is a graph theory or any AI model, which gives us the better results through the perfect through the less computation time. We can use any model, and we have to make sure that all these fixes, all these design modifications that we are doing is perfectly working as expected. Okay, then whatever we discussed initially, that okay, if I cover first problem was that the data cannot be early, cannot be late, it has to be on time. So that is covered. Second is that combination of voltage, temperature, aging, that is also covered. So we are covering all the combinations. Third, we are covering the power related features. Okay, we are making sure that the power is aligned across all the combinations. And the fourth is that we are not having any kind of manufacturing defect. So initially, if we don't use these kind of models, the number of the combinations that we have will increase drastically, and we cannot even have that kind of resources to do the simulation. But if we use these kind of AI models in these cases, we can in future, I am hoping that we will have more and more such cases where the combination can, let's say if I have 600 such combination right now, I can do it with, by using these models, we can do it with 100 such combinations. In future, it can also be possible to do it with, let's say, 80 combinations. It will make the chip design cycle very, very fast. Okay. And the last thing that I wanted to cover is on the design modification side is that so when we are doing this kind of logic analysis, right, what we have to do is we have to make sure that whatever the changes we are doing, right, it is aligned with my design. Okay, it has to be physically, it has to be possible. Like I cannot change any cell or add or remove any cell without considering the physical parameters. Physical parameters is nothing but these three things. Okay, floor planning, placement, and routing. So let's say if I've decided that, okay, there is a violation, and if I want to fix any of one such case, okay, in the logic, I have to make sure that it is with the given floor planning range. It is basically the new cell that I have added. It is placed properly, and the routing, the nets, wires, right, what we call it, that has to be properly routed without any kind of hindrance. Okay, so this kind of models and this kind of advantages that we have today is that current models are current solutions that we have from EDA are working very fine, but there will be a need and there is a huge scope of opportunity for making these models even faster and how industry can adapt to the newer models, to newer ChatGPT and Gemini kind of models directly with these kind of solutions. If let's say if they can just reduce the number of fixes that I have to do in my design, that will alone will help us to identify that okay, if we can reduce the number of changes that we have to do, or if we can know upfront that okay, these kind of violations will happen, let's say in the initial stage of floor planning, we might not even have the violations once the routing is done. Okay. That is my last slide. If you have any questions or anything, please let me know. I'll be very happy to take it up. Are there any questions?
Yes, anyone having any queries? Do we have any queries, anyone? So I guess there are no queries from anyone so far. Parth, your session was really wonderful, very much informative, and I thoroughly learned the way you taught. Thank you so much. And just like me, I feel everyone has learned a lot. So,
Thank you.
hugely thankful to you for your session, Parth.
Thank you. Thank you so much, madam, for this opportunity and for giving me this chance to present.
And
So that,
like you all
yeah,
continue to make us proud of our alumni.
thank you. Thank you so much.
Uh, Now, every one of us would turn on the camera once for the group photo of the day. Yes, everyone, please turn on the cameras. Okay, so thank you so much. Here we are, ending today and calling it a day. Tomorrow, I just hope you all remember that tomorrow, instead of 2, we have 3 sessions. Our first session will begin at 2 p.m. Kindly note down the change in the schedule tomorrow. We have last 3 sessions tomorrow, and the first one will begin sharp at 2 p.m. This is one important thing for you to make a note. Another thing I would like to share is the link of the mock test has been already sent to you, and please try to attend the mock test in order to score more, because that will give you a clear idea of how to appear for the test tomorrow. So allow yourself a good practice through the mock test, and the link of the mock test has been sent to you in your email. And
Hey,
again,
madam.
yes, yes, please. Anyone was having a query? Okay. So the links of the feedback has been sent, and
Meeting will be after 6:30, no?
what?
Online test will be after 6:30, no?
Yes, yes, it's as per the schedule only. The schedule that has been sent will follow that strictly.
Okay, ma'am. Thank you.
Yeah. Okay. So with that note, I just hope everything is clear to all of you. We are calling it a day. Enjoy your evening. Good night.